So in today's lesson, we're looking at ideal gas molecules. And there's three learning objectives, actually two. Understand that molecules in a gas have random motion that can exert a force and hence a pressure on a wall of a container, and then use the relationship between pressure and volume of a fixed mass of a gas at constant temperature, so P1, V1 equals P2, V2. So in terms of molecular movement in gases, so gases consist of basically molecules jumping around in random motion. And that means that due to all these collisions happening in the atmosphere, they are changing, or the direction is changing in a very unpredictable way. It's random. Okay? And this is the concept of Brownian motion. So if you observe through a microscope the motion of pollen grains suspended in water, also smoke particles in air, the grains jump around, okay? And a similar observation here, as it says, can be seen with smoke particles suspended in air. Okay? And the motion of the smaller invisible air molecules must also be random because they're basically colliding against the larger visible smoke particles. Okay? Because the smoke particles are larger and move more slowly due to their greater mass. They're bigger. So in terms of gas pressure, particle theory says the following, okay? Gas particles or molecules are moving in constant random motion, and when a molecule hits the surface, it's going to exert a force. That's Newton's third law. Every action has an equal and opposite reaction. And it's going to cause that particle to change direction. And the pressure exerted by the gas is equal to the total force exerted by that molecule over that particular area. So remember, because pressure equals force divided by area. Okay, that makes sense. So Boyles Law states that the pressure of a gas is inversely proportional to its volume. Okay, so as you decrease the volume of a container, the pressure is going to increase. Okay, or the volume of a gas doubles as its pressure halves. And the key is, though, that Boyles' law only applies for the gas if the mass and the temperature are the same. They're kept constant. They don't change during the compression or decompression while the volume's being changed. Okay, and therefore you can use the following equation if the temperature and the mass are constant. P1 V1 equals P2 V2, where P1 is the initial gas pressure, P2 is the final gas pressure, V1 is the initial gas volume, and V2 is the final gas volume. So how do we check Boyles' law experimentally? Okay, so this is quite antiquated equipment, but still, you record the initial volume and pressure of gas in a particular tube. Okay, and you'll see that the tube is connected to a foot pump. Okay, so you use the foot pump to decrease the volume of gas in the tube. And then you record the new volume and also record the new pressure. You then use the foot pump to obtain further sets of volume and pressure measurements. Okay, because basically what you're doing is by adding the foot pump, you're increasing the pressure, but decreasing the volume. And what you get is a graph like this. Okay, so if you plot a graph of pressure against 1 over volume, important 1 over, so it's the inverse of volume, you get a straight line through the origin. Okay, so that basically also says that the pressure times the volume is going to be a constant for that particular gas. Okay, so P over 1 over the volume is a straight line because it's an inverse relationship. Pressure is proportional to 1 over the volume. Okay, but if you do a pressure against volume graph, you get a funky graph like this, which is an inverse relationship. Okay, it's a curved line. And the line does not intercept on either of the axes. And that is the first gas law that you'll come across. And next lesson, we will look at another gas law relating the temperature to the pressure.